Well, thank you so much for the kind introduction. It's a pleasure to be here. Thank you so much for attending my talk. I'm going to talk about some of our work on machine learning for systems. This is a team that a colleague of mine, Anna Goldie, and myself co-founded 2 years ago at Google Brain, and I'm going to talk about some of the work and approaches that we have developed over the past couple years and where we are going from here. So, first of all, a little bit of motivation. If you look into the success of machine learning in the past decade or so, you'll see that a lot of this success is because of the extremely powerful computer systems and computer hardware that have been developed. Our vision is that it's now time to return the favor and basically develop new systems and chips using machine learning. So machine learning itself can help develop better AI chips and systems, so in turn, we can run more powerful machine learning algorithms. Now, let's take a look at this chart released by OpenAI this year that says a very interesting fact. Between 1959 and 2012, there was a 2-year doubling time for the amount of compute used in historical AI results. Since 2012, and that's the year that deep learning really started working, this doubling time is now happening every 3.4 months. And by comparison, Moore's law had an 18-month doubling period. And Moore's law has been dead for 15 years now. So this shows us how important it is for us to develop better systems and chips so they can keep up with the computational demands of AI. But it turns out that chip design is a really complicated task. Here, I'm showing you the complexities of chess and Go, two canonical examples of hard games previously solved by AI. And as you can see here, their complexities are still orders of magnitude lower than that of chip placement problem, which is only one problem in chip design. And chip design has so many other stages for development. So we are really dealing with a new level of complexity in designing chips and systems. Now, for the rest of this talk, I'm going to focus on a specific type of problems, and that is machine learning on decision-making on graph-structured data. And the reason for that is this type of problem appears in many different fields in systems. For example, computational graph placement, chip placement, and data center allocation optimization are all examples of decision-making on graphs, where the input, for example, in computational graph placement, could be a TensorFlow graph, and the objective is to place this TensorFlow graph onto the hardware that we have. In the chip placement problem, the input is a chip netlist, also a graph, and the goal is to map the nodes like macros and standard cells of the netlist onto a 2D grid. In the data center allocation task, the input is a job workload graph, and the objective is to place the workload onto the data center computing nodes. So in all of these problems, we are taking a graph as input, and our task is to allocate the nodes of this graph onto some resources that we have. So in this talk, I'm going to talk about some of our approaches to tackle problems in decision-making on graphs. In the first part of my talk, I'm going to mention our work on policy gradient methods for device placement and reinforcement learning approaches for large action spaces and long horizons. And in the second part of my talk, I'm going to talk about learning approaches to large graphs that appear in systems, because a lot of times the graphs that we have are millions or even billions of nodes, and we need to have ways to kind of break down the complexity of the problem by partitioning the graphs and solve the subproblems. So let's start with sequential decision-making task. So the first problem that I'm going to talk about is device placement problem. Let me first define what this problem is. A lot of the success of recent deep learning models is because these models are becoming really, really large. And in order for us to run these models fast, we need to map this model efficiently onto the computing nodes that we have. For example, this could be multiple cores of a CPU, it could be GPUs or TPUs. So the device placement problem has to do with how we can take a computational graph and map it to the computing hardware and resources that we have in a way that once we've done this mapping, the graph runs as fast as possible. So our approach to this, and this is a classic problem, which is known to be very complex. It has an NP-complete nature to it. The way we tackled this problem was by posing it as a reinforcement learning policy optimization method. And the way it worked was that we trained a policy that takes a neural network, a computational graph as input. It also takes the available resources, for example, a bunch of CPUs and GPUs in this case, as input. The output of the policy is an assignment of the nodes of the neural net onto the resource devices that we have. Once we have an assignment by the policy, what we can do is that we go ahead and measure the runtime according to the proposed placement. And this measurement can be really fast because for training a neural net, we need like thousands of epochs of iteration. Here, we only need one batch runtime measurement. So it can be really quick. Once we measure this runtime, we go back and use it as a reward function to optimize our policy. So the policy next time generates new assignments of the nodes of the neural net to the devices that we have, and we go over this loop many, many iterations until we find the optimized placement solutions. Once we find that, then we can go ahead and use these models in an optimized way, whether we use them at inference, in production, or during training for different hyperparameter tuning and such. Now, a little bit more about how this policy actually works and how it takes the graph as input. So here I'm showing you a hierarchical architecture for the policy. On the input side, we pass information about this graph that we want to map to the hardware. The information here are passed through ops, and by what I mean by op is the nodes of a neural network. It could be a convolutional node, an LSTM, a feed-forward, an RLU, or such. So we can pass information about the type of the node, about its adjacency information, about its size of input, size of output. So that's where we can encode information about the graph into the model. Once we pass it to the model, here we first group the nodes because we wanted to reduce the complexity. We can have tens of thousands of nodes. So we first group the nodes into a few hundred groups. And then in the second layer of the hierarchy, for those of you who are familiar with this architecture, is a sequence-to-sequence model. So it takes the groups as input, and on the output side, one by one, we can predict onto which device each group goes to. So for example, group 1 goes to GPU 1, group 2 goes to GPU 3, and so on, right? Once we have all of these placements, then we can go ahead and measure the runtime and see how well we are doing. We use that as a reward function to go back and optimize the parameters of the policy. And I go just a little bit over how we actually do this optimization. So the algorithm that we use for this optimization is based on the reinforce equation. Basically, what we are doing here, we are training a policy in order to optimize the expected runtime given the distribution of placements developed by the policy. So we are tuning this distribution in a way that the generated placements are optimized towards a reward function, which is runtime in this case. We are doing a hierarchical approach, so we first learn groupings for the operations in a node, and once we learn that, we condition the placement on the groups that are generated, and we go from there. What I'm showing you here is one of our experiments on an LSTM encoder-decoder. This is a model that is used for example, a neural machine translation for translating language from one to the other. Each of the colors that you see here is a different GPU, and the white color is a CPU. And basically, what I'm showing you is how the computational ops onto this LSTM model are mapped to these different GPUs. And as you can see, this is not a very intuitive placement, at least for a human eye. But there are some interesting properties. For example, the model learned to put the embedding on the CPU. And we already know that CPUs are much better suited for dealing with the embedding layer than the GPUs. And it turns out this model works better than our baseline placement, which was something that these models are used in products. So there is a lot of effort to make the placement optimized. We looked into this and tried to understand what the policy is doing by coming up with this non-intuitive placement. And it turns out that the policy is actually optimizing for load balancing in this case. I'm showing you the workload of each of the GPUs on the left side for the placement generated by our policy, on the right side for a placement generated by a human expert. And as you can see, the workload is much more balanced in our placement, and the reason for that, and the reason that the human expert one is not very balanced is that we optimize, the optimizations were done for the forward pass because we have these nice APIs that we can assign device placements on the forward pass, but it turns out that in deep learning, roughly twice the computation comes from back propagation optimization. So the forward pass on the right side is roughly still balanced, but if you aggregate forward and backward pass, it's not. So that's how we were getting improved runtimes for training in this case. We looked into another model here, an inception. It's a vision model, and each of these units are convolution models, and each of the colors again are a different GPU. And there are some other interesting properties here. For example, the model kind of learned some sort of parallelism across the branches of these computational units, and this is without us telling anything explicitly to the model that we like parallelism in the assignment. Everything we showed to the model was just the input graph and the runtime. So the runtime was the only signal that it could use to kind of figure out these implicit trade-offs between computation and communication. In this case, we did another kind of comparison where our baseline was completely data parallel, meaning that for our baseline case, we took an inception model and we put one inception on each of the GPUs that we had. So we did like this trick of parallelizing a batch across 4 GPUs. So in this case, we were completely, by design, making the computation balance across the GPUs. And on the right side, we see our policy that is not very balanced in this case, but again, we were getting better runtime results from the baseline. We looked more into this, and this time we looked into the amount of memory copies that is being done on our placement versus the human expert placement that was completely data parallel. And it turns out that in this case, the policy learns to optimize more for the amount of mem copies, and that way it can manage to optimize the runtime end-to-end more than our baseline, which was a very interesting property, this trade-off that it found on its own just by looking into the reward function that's runtime. Now, since a few months ago, we decided, and that was our goal from the beginning, we decided we want to train policies that can generalize across graphs, meaning that our end goal is we pre-train a policy on some training data, but whenever we see a new graph, a new TensorFlow graph, we can on the fly just apply the policy and get optimized placement without any further training. So we can rewrite our objective function as expected value of reward, which is correlated with the runtime, but this time not only on the policy, but on a given graph, but also on a distribution of graphs that we get as input. And it turns out for solving, we just first tried just going with what we had before. We trained policies on our hierarchical architecture, and we tried it on new graphs. And it turns out that that doesn't work on its own. And to some extent, it's clear because we were hand-coding a lot of information about graph adjacency and graph nodes and such. And these information, like graphs have different sizes, different number of nodes and such. So it's not really natural for the policy to generalize. So we had to do other work here. And a big part of it was related to using better ways to represent graphs. And that was to use graph neural networks. A way to embed adjacency, like 1-hop, 2-hop, 3-hop, and such adjacent information of the nodes of the graph, and basically training language models for the operation types in the nodes of the graph. So then the model has a very good understanding of how the graph is represented, so that if it sees a new graph, if there are similarities between what it has seen before during training, it can match those similarities and reuse those for finding optimized placement. And so we use GraphSage. It's a graph neural optimization method for embedding graph information. And on the placement side, this time, because it's 2019, we use Transformer XL, which is a encoder-decoder architecture that can handle really large number of nodes. So we didn't even need to do a hierarchical approach at this point. And it turns out that this model works. And we were very excited to see this because it's one of the first times that we see generalization on policy on a very complex data set such as computational graphs. Here you can see the black bars. That's where we train the model. We call it GDP, Generalized Device Placement, on a network from scratch. So that's the best we could do for that model. The red one is when we take this model, pre-trained on a training data set, and then use it at inference time without any training. And as you can see, even though there is a gap between the red and black in terms of runtime, lower runtimes is better, but still this was without any extra effort in terms of our training the policy on that side, and that's very encouraging. And very recently, we have seen that on some benchmarks, we can even improve the placement by using this pre-trained model, which we are really hoping to push more for that, because our belief is that if the policy has seen a ton of graphs in training data, it must do better on a new unseen graph. So if you're interested about our line of work on placement, please take a look into these publications that I put here. Also, you can see some of our results. They are used on like some of the latest machine learning, deep learning models in speech, vision, and text that you can see here. So this was like a wrap-up for the first part of my talk. Now I want to go to the second part, where I talk about sequential decision-making tasks and policy optimization for large action spaces and long horizons. So in device placement, there was this nice property of the number of devices that we have. For example, we have 8 GPUs or 10 TPU cores. Usually it's not a whole lot. But in a lot of other systems or chip design problem, for example, in the chip placement problem, we can have millions of locations for placing the nodes of a graph. Because imagine we are placing every node on a 2D grid that has millions of nodes on a 2D grid, right? So our action space is much larger, and this makes optimization a lot harder. Our solution for tackling this other type of problem with larger action spaces was to go from the discrete domain to the continuous domain. So we modeled the action space with a continuous probability function. And in order for us to be able to search this space, we also had to come up with better search methods. And in this case, we chose to design 3 search methods, in particular Monte Carlo tree search methods in order to kind of augment the policy to be able to search these large spaces. So instead of training a policy and using the reward to update the policy, we train the policy, use a tree to expand the policy, generate better trajectories, and then go back to update the policy from there. To give you a little bit of background about how the tree search works, imagine we have a policy that kind of gives us a probability of, given a state, gives us the probability of taking an action from that state. We can take this policy and expand it via a tree in 4 stages. In the first part, which is called selection, we look into a state by the policy that the area around it, for example, hasn't been explored much, or a state that has a high reward and it has potential to be explored more around. Once we find a state, here we call it a leaf node, we sample a bunch of actions from the policy, from our continuous policy, to make the branches of this tree. So each of these branches are sampled actions from the policy. Once we have those, we can kind of do some sort of simulation, like a Monte Carlo simulation, to see the goodness of those actions taken given a state. And once we have those goodness values, we can backpropagate all the way to the root state to see how, to kind of have a look-ahead approach to optimization of a given state. So basically, given a state, we can always easily find the reward for the next action that we take. But it's much harder to see the reward after we are done optimizing all the actions. So this kind of helps us do a kind of a beam search approach to see more of our policy state. And in a recent work, what we did was we took a policy that was trained, and we used that policy to generate Monte Carlo tree search trajectories and use that to further optimize the policy based off. And it turns out that this model actually works very well. Here with the red line, I'm showing you the case where we only optimize the policy. And in the blue line is where we take the policy and augment it with a tree search approach. And these are done on 6 of the Mujoko environment. This is like a very established baseline for policy optimization methods. And as you can see, by using this tree, we can really make a big difference in terms of our returns and the goodness of the policy after we use the tree search optimization. There are a lot of tricks that go into this method that makes a large searching over the large action space possible, which I don't go through. But there was this one important one that has to do with the depth of the tree. As you can imagine, in a lot of decision-making application, each decision that you make, imagine you go one level down the tree, but if you have 1 million decisions to make, the depth of this tree can be really, really large. So it makes it really complex to optimize the tree and go back to optimize the policy. Here, with the black circles, I'm showing you a policy trajectory, and with the red lines, it's like a tree trajectory. So it can diverge. The tree and the policy can diverge. So what we did here was to take a middle ground approach where we don't do the policy only and we don't do the policy tree search. Instead, we do this depth parallel approach where we take samples from a trajectory of the policy. We use that samples to generate intermediate tree that we don't have look ahead all the way to the end, but we have look ahead to very smaller intervals. And this also helps us to parallelize the trajectory generation by tree. And this really helped this method work for us. And if you are interested about it, I put some links in the end to our open source code on this approach. Now let's go into the second part of my talk, which is learning to partition large graphs. So a little bit of motivation. The goal of partitioning is reducing the complexity or breaking down a problem into smaller pieces so we can optimize those smaller pieces more efficiently. There are many applications for graph partitioning. It's a classic computer science problem. VLSI design, device placement, social network distribution and placement is some of these examples. And basically our approach is to partition a graph with millions of nodes to thousands of groups, and then do the decision-making optimization onto the groups instead. Now, here I'm showing you the normalized cut objective, which is a very intuitive graph partitioning objective. Basically, the goal is to partition a graph into groups that have roughly the same number of nodes. So each group has roughly is balanced, have the same number of nodes, and the other objective is to minimize the number of edge cuts across the groups. So the normalized cut objective, as you can see here, is basically trying to optimize for balancedness while minimizing the edge cuts. So our approach here was, because we are taking a learning approach downstream on the graphs, can we make the first place that we enter into a graph optimization, which is the partitioning, can we take a learnable approach to that as well or not? And it turns out that we can, and we took a very simple approach to graph partitioning, and that was to train a neural network that takes the nodes of the graph as input, and on the output side, it predicts a probability of assignment of a node to a cluster. Let's say we have a cluster of size 10. The neural network predicts, say with probability 0.8, the node goes to cluster 1. With probability 0.1, it goes to cluster 2, and so on. And then once we have it, we can sample from that probability and do the assignment of nodes to the clusters. And the question now is how we can train this neural network that does a good job in clustering. And here I'm showing you two nodes, for example, node Vi and node Vj. And let's assume the probability of them, node Vi belonging to cluster C, is predicted by PCI. Same for Vj. Then we can write the expected cut of cluster C with respect to those two nodes, as you can see in that. So basically what we are doing is, instead of counting how many edge cuts we have, we are looking into the expected number of edge cuts using these probabilities. Now we can take the normalized cut objective and define this unsupervised loss function that basically tries to minimize the expected number of cuts, and also tries to balance the clusters, the expected number of nodes in a cluster. And to show you an example, and a toy example of how this works, let's assume our nodes are these images, and the graph between the nodes are these implicit, like the images have some distance from each other. And our goal here is to find cluster 1 and cluster 2. Cluster 1 is obviously cars, and cluster 2 belongs to roosters, I think, in this case. So we train our model. We call it CNC, clustering by normalized cuts. It takes the nodes, and for each of the node, it outputs a probability of belonging to cluster 1 and a probability of belonging to cluster 2. And on the right side, on on C, you can see that as we train this CNC loss function, this unsupervised loss function, as it is converging, it will converge to the normalized cut objective, which gives us a normalized cut objective is the objective that gives us the balance and minimize edge cut graph partitions. So as our loss is converging, the probabilities become tuned, and this gives us optimized placements. An interesting property of these partitions, of course, we compared it with classic, and there are a ton of methods for graph partitioning and clustering. We compared it with spectral methods and off-the-shelf tools such as HMetis and such. And for more information, you can take a look into our paper and also the open source code that will be open source code by the end of this month. But an interesting property here is that for the first time, we could train models that can generalize graph partitioning, meaning that if we train a partitioner on a set of training graphs, we could on the fly partition a new graph coming from that distribution, which none of these off-the-shelf existing methods could do, because and the reason we can do it is we have the gradients and we have the weight parameters to kind of memorize that. And with that, I'm going to conclude my talk. So in this talk, I talked about two sets of approaches that, with some motivations on why we care about this in systems and chips. I talked about sequential decision-making optimizations with policy gradient methods and RL for large action spaces and long horizons. I also talked about learning-based approaches to graph partitioning and how they can help us to generalize. Here are some of the papers and some of the open source code that we have that you can take a look if you're interested. And with that, I can conclude my talk.
Hi, great talk. The CNC method, did you find similarity? Because it looks like principal component analysis. Could you try to solve as a matrix? And did you compare the result?
Principal component in terms of like cutting down on the images and such.
Well, you have a
so SpectralNet, which is like one of our baselines here, is a method based on not exactly principle like SVD and such, and we took a look into how we do better than that, and we were doing that in normalized cut and in also the accuracy of the clustering objective. But something that I would say that our method helps a lot is kind of we can instrument a lot of learning and embedding of the nodes of the graph easily into the model and use the convolutional methods and like LSTMs to embed information about the nodes of the graph, which is like helps us a lot with generalization and with so basically the dictionary in principal component analysis that we learned here is much more advanced because we can feed in all this information to our neural network.